So, ladies and gentlemen, are you ready? Are you ready for the most sensitive, the most accurate sensors in the entire planet? Well, the industry is ready to have them. Let's accelerate the process for having them. Welcome to the Epic Online Technology Meeting on ion traps, gravitometers, and quantum sensors. So what's keeping you down today? It's gravity! Everywhere I go, there it is. Isaac Newton noticed that too. And on Wednesday, November 3rd, we are going to explore new instruments that use quantum technologies to deliver the most accurate measurements ever made. In physics, we normally say that Earth's gravity pulls things towards its center at a rate of 9.8 meters per second squared, but that is just an approximation. The Earth's gravity is not constant all over the world and can change over time. For example, a shifting mass of water can mean a change in Earth's gravity. How can we measure these tiny changes in gravity? By building the most sensitive gravitometer to date. Here comes quantum. Atom ionics has one of the best explanations of what's happening inside a quantum gravitometer. We need a vacuum chamber containing a collection of rubidium or cesium atoms. We cool them by bombarding them with lasers from all sides to slow them down. Once the atoms have slowed down, they start behaving less like particles and more like waves. This makes it easier for us to measure the forces acting on them. And these are no longer lab experiments. Field tests have been realized worldwide. And now large corporations in automotive, space, mining, oil and gas, and defense can't wait to deploy those sensors. The meeting on Wednesday, 3rd November is going to bring together some of these companies and match their needs and dreams with the leading quantum tech in Epic. Some of these companies are Bosch, the European Space Agency, the Submarines program of the Italian Navy, Q.ANT, acquired by Trump, the leading quantum R&D center QuTech, the European quantum success story ID Quantique, and many more. But let's take Bosch as an example. In June 2019, just before the pandemic, you may recall we organized the World Quantum Photonics Technology Summit in Barcelona. We invited Janine Riedrich-Möller from Bosch to come and enlighten us, and she stole the conference stage with a brilliant presentation. Let's take a perfect diamond. Perfect diamonds are beautiful and they consist of nothing but carbon. But in quantum tech, they become even more beautiful if we replace one of the carbon atoms by nitrogen. As a result, they become highly sensitive to the tiniest changes in magnetic fields, excellent to look underground for metals, oil, or old fossils. Furthermore, governments all want to invest to get more accurate predictions of impending natural disasters. That's relevant in the Canary Islands at the moment with volcanic eruptions, but also in places like New Zealand, which is earthquake prone. These quantum sensors are so sensitive, they can even detect brainwave patterns typical in neurological disorders. They are even proposing these sensors for the early diagnosis of Alzheimer's, epilepsy, and Parkinson's. This is really a meeting you can't miss. I can't wait myself. See you on Monday, November 3 at 3 p.m. So here we are on Wednesday, November 3 at 3 p.m. I said Monday in the video and nobody complained. So I don't know if many people reached the end of the video or they just didn't like to complain. So such an awesome work. Thank you very much, all of you, for all the input and all the feedback I received on the last weeks for this fantastic and this is very important topic for Europe. My name is Jose Pozo and I'm here talking on behalf of a fantastic team of Epic staff, but also a fantastic selection of companies, 750 members of Epic. And together with my colleagues, we organize events, we provide access to the network, we help you raise capital, we have the biggest website to find a job in Photonics, jobsinphotonics.com, and we also help you with your market data for the strategic decisions of your company. Remember that today is Ion Traps on the 1st of December. we have our star online technology meeting on quantum tech. It's going to be on large-scale qubit generation, comparing photonics, ions, and superconductors. Do not miss that one, but also remind you that EPIC is a photonic association. We have our photonic online technology meetings, and on Monday, 8th of November, we talk about new developments for microwave photonics, generating clean RF carrier waves using photonic integration. This is a very important topic for 5G. But today is all about quantum tech, and it's all about quantum sensors. First of all, I would like to thank the cooperation of the QBN, the Quantum Business Network, but also our media partner, Electro Optics. Thank you very much for promoting everything we do in the magazine Electro Optics. You're doing a fantastic job. But most important, this meeting wouldn't be possible without the support of our sponsors today. First, all the way from Finland, Modulight. Modulight is a semiconductor laser manufacturer who provides MBE growth all the way to assembly of fully functional solutions, developing even solutions ready for clinicians. iXblue, coming all the way from beautiful Grenoble. iXblue is a specialty fiber manufacturer providing components, system, and instrumentation for scientific and industrial applications. Remember, they just acquired new Quants. And finally, all the way from Copenhagen, NKT Photonics, which provide ultra-stable mode-hole-free lasers with extremely narrow line width, high power, and wavelength conversion for trap atom, quantum computing, and sensing applications. This is all very important, but the most important announcement today is the first online technology meeting of our new quantum expert, Dr. Panagiotis Vergyris. Panos, thank you very much for being with us today. What's going to happen over the next 2 hours?
Thanks, Jose. Thanks. Hi to everybody. I'm new in EPIC, and I will deal from now on with the quantum industry related to photonics. So for the next 2 hours, we're gonna have fantastic speakers from Bosch, Quantique, Italian Navy, Delft University, and QuTech, actually QuTech and Q.ANT. Just to a small detail, Jose, I don't know if you are informed, but Janine might join us later. So in case it's not ready, please, we can start from the second speaker. And we have people from all the supply chain, companies from all the supply chain, covering everything related to quantum sensing. So please, Jose, if you...
Thank you very much, Panos. Welcome to the jungle. Welcome to EPIC. Welcome to working non-stop for the photonic industry. This slide shows that we really have the entire supply chain in the meeting today, from lasers to photonic integrated circuits, from control systems all the way to quantum computers and quantum sensor solutions. Thank you very much, companies like QuickS, like Q.ANT, for being here today. But also, we'd like to say that this slide only corresponds to the companies who registered for the meeting today. So if you're an EPIC member and your logo is not in this slide, only means that you forgot to register. Don't let it happen again. Please register online for the meetings that are relevant to your company. Also, this meeting is live streamed in YouTube. So hello, YouTubers of the world. If you want to get in touch with any of the participants today, all you have to do is send me an email, jose.pozo@epic-asset.com, and I would love to make that introduction. And this is, of course, also valid for the people here with me in the Zoom room. There's an internal chat, so use it, abuse it. I want to see you typing all the time because I want to get in touch, or I want you to get in touch with everyone. If somebody doesn't know Bruno Leone from the European Space Agency and you want to connect with him, this is your chance to connect with ESA expert on quantum sensors. But today is all about success stories and how to help them accelerate. And we have to start with one of the most important success stories for quantum technologies in the world. I'm referring, of course, to the company Quantique. We all know, we all love Quantique. If you have a PhD in quantum physics like me, you love Quantique. Thank you very much, Martin Felle, for starting the meeting today with the biggest success that we have in the quantum industry in Europe. The floor and the attention of everyone goes to IDQ, goes to you, Martin.
Wonderful. Well, thank you, Jose, for that warm introduction, and hello, everyone. You give me just a moment, I will share my screen and I'll show you what's happening. And here we go. So I'm very happy to be here today. Can everyone see my screen first?
Crystal clear.
Crystal clear, lovely. I'm happy to be here today to talk to you about photonic quantum sensing. I'll go back a bit. So my name is Martin Felle. I'm a product manager in the quantum sensing division of Quantique, and we are based in Geneva. Our goal is to help enable innovation in this surging quantum technology industry right now through high performance single photon detection, counting, and instrumentation. In particular, I'll talk about our keystone product, how these superconducting nanowire single photon detectors are being used today to advance quantum computing and quantum internet applications to new heights. It's all very exciting. I'm sure you've heard of IDQ, but for those who haven't, we are in the quantum communication business. ID Quantique was founded in 2001 as a spin-off of the University of Geneva by 4 renowned quantum physicists with the ambition to develop single photon detection systems and become market pioneers in quantum randomness and quantum safe communication. With our headquarters in Geneva and offices in South Korea and the USA, the company employs more than 100 people with still a strong focus on R&D and product development with 50 engineers and scientists. The company itself is arranged into 2 divisions, the Quantum Safe division, which addresses current security applications based on QKD even today, as well as the Quantum Sensing division, which is striving to build and enable the companies to develop the fundamental building blocks for a future quantum internet. So detecting single photons is hard. I don't know if you've tried it. Not because they are weird, strange wonders of quantum mechanics, but there's simply too many of them. You have a similar issue trying to count the drops of water in the ocean or the number of atoms in this pencil. It's a relatively simple matter to turn a single particle of light into a machine-readable signal. Photomultiplier tubes, PMTs, and single photon avalanche diodes, SPADs we refer to them as, are examples of detectors that can rapidly turn a single photon into a large measurable number of electrons, very much like the clicks of a Geiger counter detecting particles of ionizing radiation. However, the state of the single photon detection art is very much the superconducting nanowire detector. In these devices, a single meandering line, you can see in the top right here, a single meandering line of superconducting material is held close to the superconducting threshold where a single photon creates a localized but measurable spike in resistance. And this method is fantastic. It provides nearly ideal, high efficiency, super precise timing, ultra low noise, which lets them operate a much wider range of photonic experiments and applications to their SPAD and PMC counterparts. So how efficient are our detectors and why is that important? Well, the answer there is that we can routinely reach above 95% system detection efficiency. So you're seeing 95% of the photons that are coming onto your detector on devices that are commercially available today. Furthermore, they can detect across a really wide wavelength range, so hundreds of nanometers from less than 700 nanometer to well above 2 microns, comfortably there, including some of the dead ranges that some of the detector materials don't cover today that well. Let's say around 900 to 1000 nanometers. Silicon and InGaAs are a bit dead there. And as well, operating at cryogenic temperatures means that the noise performance is really exceptional. Depending on the wavelength, because there are more black body photons towards kind of longer wavelengths, we'll see less than 1 dark count per second for the visible detectors and less than 100 dark counts per second at telecom wavelengths, around 1550. And this high efficiency and low noise allows you to have really stellar signal to noise ratio, which is important for any applications where you're requiring multiple single photon coincidences, such as a quantum repeater, where you might be looking at up to 4 coincidences. In a recent piece of work here that I'm showing here that was done by the ICFO Institute of Photonic Sciences in Barcelona by Samuel Grandi, Dario Lago Riviera, Helena Rakonjak, and Alessandro Seri in the group of Hugo Riedmatten, and they demonstrated successful entanglement of remote quantum memories between a telecom wavelength photon and an on-demand multi-mode quantum memory, which they did with a set of our ID281 SPADs, which were spec'd at greater than 80% efficiency, less than 14 dark counts per second, all at 1450 nanometers. And that allowed them to collect photons as efficiently as possible with as little background noise as possible, which led to the successful results they had there. However, it's not just enough to see all the photons, you also need to resolve them in time, which is again where the ID281 can help. SPADs are fantastic here. They have incredibly high timing precision. The timing interval error of these pulses that get generated, i.e. the timing jitter, is routinely below several tens of picoseconds. So you have a resolution of tens of picoseconds in your setups, which can be critical in photonic applications with features that are very short-lived in time, such as your systems with short fluorescence lifetimes or coherence times. Thanks to this low timing jitter and the high timing precision, Zhaohui Ma and Jiang Chen with the Laboratory for Quantum Enhanced Systems and Technology and the Quest Lab at the Stevens Institute of Technology in the US were able to successfully demonstrate a really high fidelity and low noise, ultra bright telecom wavelength single photon source. For this, they used an arrangement of our ID281 SNSPDs with greater than 85% efficiency, this time paired with the ID900 time controller, which is our in-house manufactured single photon correlator, where we have up to 5 channels and also serves as, it's a time tagging device essentially with delay generation possible. And it stands aside uniquely for having its own internal logic, which can do real-time quadruple coincidence filtering without having to post-process terabytes of data after the fact. So being a bit more forward-looking, what is our vision of a quantum internet? Today, we're selling off-the-shelf QKD systems, such as the XG, which was released recently. And this is kind of the core focus of IDQ, demonstrating point-to-point quantum channels as they are, and guaranteeing the long-term confidentiality of data. Sort of right now, and as well in the immediate future, we're seeing improvements in quantum imaging, super resolution microscopy, all of this driven by laboratory research, which IDQ is a strong enabler with their really top-notch detectors and correlators. In the next 2 to 5 years, we'll be looking at improving the quantum comms infrastructure, getting things more generalized, more complicated networks, longer channels, higher bit rates, higher key rates, for which we need kind of quantum repeaters, strong quantum memories, better quantum light sources, integrated as much as possible so it can be sort of shipped into a data center and run fairly reliably. And as well, we might want to have sort of detectors and arrays that we can send up to space for free space QKD and space-based satellite QKD. Then looking a bit more forward-looking, we want to have very strong integrability of quantum networks between different technologies, different providers, different types of qubits, different quantum communication schemes to manage the work there. And above and beyond 10 years, we want quantum communication to be the standard so that there's a real quantum internet out there where we can do distributed schemes of quantum computing and relying on the development of quantum qubit transducers, sort of interconverting flying and stationary qubits, etc. And so IDQ is positioning ourselves as an enabler for this progression towards a quantum internet. It's really very much our mission, our vision, and we are supporting the quantum technology industry in reaching this ambitious and exciting goal. So that's, I think, about all I have time for today. I'd like to open the floor up to any questions, or I let Jose take back the reins. But thank you very much,
Martin. Thank you for existing. Thank you, ID Quantique, for existing. I really needed this company in the network to show that there is a roadmap for leading quantum tech from the industrial side. And thank you for all the work that you're doing with universities. This meeting is about quantum sensors. I am sure you knew that. So I would like to ask you, there is 750 EPIC members here. They provide lasers, detectors, integrated photonics. Tell me a couple of items in your Santa Claus Christmas list. The EPIC question: what can you do for them? What can they do for you?
I mean, so the real challenge we have is sort of sharing a good level of awareness and understanding of quantum concepts. We're dealing, as it relates to single photon counting, we have a broad range of people and a broad range of specialities, whether it's microscopy labs, biology, LiDAR applications, quantum information, and they all use different words, different terminology, they speak different language, they understand photonics to different degrees. And so what I'd love there is kind of any insights or any even help on how we can help reach our audience better.
And we will help. Look, I have three questions for you in the panel. The European Space Agency, the R&D Center, the top R&D Center QuTech in Delft, and Fraunhofer HHI in Berlin. So let's go to them and see what's on their mind. Let's start with the European Space Agency. Bruno, thank you very much for being with us today. Tell us what's on your mind. How can we help IDQ being even greater than already is?
Actually, I had a silly question about quantum internet. I'm not aware of anyone in the European Space Agency considering this yet. Anyway, so I wanted maybe a brief summary of what it will bring to society. So apart from the inbuilt security of QKD. Communication between, say, quantum computers when they exist, etc. What is the added value of having a quantum internet?
Thank you, Bruno. That's an excellent question. What is the added value of a quantum internet? So I think what's important here is to define what the quantum internet is. It varies depending on who you ask. There's a plethora of different definitions, but in our understanding at IDQ, it's a generalization of sharing arbitrary quantum states and arbitrary quantum computing architecture at remote locations. So QKD, quantum security, is a first demonstration of a quantum internet. So point-to-point sharing of individual qubits is about the simplest quantum channel you can implement. But in the future, this would be kind of multi-photonic, multi-qubit states, arbitrarily high. And the benefit here is that you might have, it's not just about security, but quantum security is a good driver for the time and for here and now. Basically, quantum computing itself is going to have a lot of enabling
Bruno Leone, we're going to have an entire meeting on quantum internet in the next quarter. So let's stay on quantum sensors, and I want to come back to you, Bruno, later after the couple of presentations to see what are in quantum sensing, what kind of things we can do with ESA. But Martin, there's another question for you coming all the way from Delft. Toeno van der Sare. Goedemiddag, Toeno. What's on your mind?
Hello, everyone, and thanks for the nice talk. I actually had a bit of a technical question on the superconducting photon detectors. So I wonder how they compare to avalanche photodiodes. I understand that they work better in the infrared, but can you also say something about the maximum count rates and the efficiency of the detectors in the visible compared to the APDs?
Yes, so the recovery times of SNSPDs are typically a bit better than APDs, but in the visible range, silicon APDs do work quite well. But you see better noise performance, better jitter, and better efficiency, of course, for SNSPDs. One region which I didn't explore in the talk, but just there. So you're looking at maybe a couple of megahertz for APDs in terms of max count rates. SNSPDs, you can see up to tens of megahertz before you start to saturate. We are actually working on new sets of, well, they're commercially available today, multi-pixel channel SNSPDs, which have kind of several sub-pixels per detector channel, where we've, in devices analyzed, investigated by the University of Geneva, they saw count rates going up to 200 megahertz before they were saturated.
And is one of the goals also to bring the price range into the same range as the APD? Because I think now they are maybe 2 orders of magnitude or maybe 1 order of magnitude more expensive.
Absolutely. So we're always looking to improve the product, reduce the size, complexity, power requirements, as well improving the yield of the materials that go into the devices themselves. Although one thing to note is that actually in terms of pricing, once you get beyond, so SPAD devices are typically one detector per device, but the SPADs, we sell up to 16 channels per device for the moment. So the price point starts to become quite attractive, especially considering the significant improvement in performance.
Of course, Martin, this is a collaboration meeting. So how cheap you can make your device is irrelevant if we cannot help you make it cheaper with the rest of the company. So is there any room for cooperation, which I guess with Toeno is going to? Is there room for cooperation? We can help you for developing the next generation. Martin.
Absolutely. I think, yeah, I'd love to hear your thoughts on how we can make this better and potentially work together. Because we've
Next question in the room comes all the way from Berlin, coming from a person who means a lot to EPIC, is Martin Schell, the director of Fraunhofer HHI. Martin, thank you very much for being with us. What's on your mind?
Thank you, Jose, and thank you, Martin, for the excellent presentation and the good market success with ID Quantique. So my question concerns PsiQuantum. They have announced a couple of months ago their partnership with Global Foundries, and if I understood that correctly, that they say that they require some 45 or 90 nanometer wafer technologies in order to make decent arrays of superconducting nanowires. What do you think of that? Will you go the same way, or is it really necessary to go to these very expensive technologies to make good arrays? Or?
So I think PsiQuantum is taking, I think they're taking a very ambitious approach. So they've got lofty goals. They want to see a very strong performing quantum computer before they have any kind of intermediate products going out. And they want everything to be kind of integrated as much as possible, which means, yeah, getting, I guess, more complex cryostats, things that work on kind of silicon integrated systems, and yeah, and things that kind of work with waveguides and such on. But yeah, my personal thought there is that kind of the coupling efficiencies would be potentially too parasitic for kind of nice general quantum computing schemes, linear optical quantum computing schemes where, yeah. And this is something we think about. We sometimes get a request of, can we make room in our cryostats to put photonic crystals or waveguides in there? Generally for us, though, the demand hasn't been high enough for us to do a redesign based on this, because we're trying to keep the form factor as compact as possible, rather than adding an extra thermal load and creating higher cost and space requirements.
Thank you very much, Martin.
Thank you.
The next question comes from CSEM. I would like to point out here in the supply chain, Amir, you can see that the lithium niobate foundry by CSEM is here in your supply chain. So thank you very much, Amir, for what you're doing lithium niobate in Europe.
Thank you.
In foundry services already from CSEM. Amir, what's on your mind?
Yeah. Hello, Martin. Thank you so much. It's nice to see you. Again. Actually, I gotta repeat the same question I think I asked you a few days ago. Is that are you going toward actually integrating your SNSPs, your let's say nanowires with the waveguides, or the future routes you're still relying on this sort of free space or fiber pigtail and a sort of coupling? I think that such an integration might increase, because you have much larger interaction, sort of lengths. So it might increase both the speed, but also the efficiency of these detectors. Or actually, it reduces, footprints and then leads to higher integration level.
It could. It's not a subject that so it's something I'd be interested in actually exploring a bit further. So maybe if you wanted to connect offline.
Absolutely.
Yeah, but no, we haven't explored this fully yet.
I love when you connect offline, but I also love what Amir is doing. The first foundry of thin lithium niobate for photonic integrated circuits is now in CSEM. Congratulations, Amir, what you have achieved. Later, because I really want to start with quantum sensors. Amir, sorry for that. When you are friends, you can get these kind of things. I would like to start now with the end user side. We go to Italy to meet Simone Riviera from the Submarine program of the Italian Navy. He really wanted to talk today because they are very interested about quantum sensors. They're doing extremely interesting activities for the rest, and I think we can help. Simone La Riviera, grazie mille. Thank you so much for taking the end user side at this important meeting. The floor and the attention of everyone goes to Italy, goes to you, Simone.
Thank you very much for inviting me to this online meeting. I'm sharing my presentation. I hope you are see my presentation now.
Clearly.
Okay, so good afternoon to everybody. It's a pleasure for me enjoying this online meeting. I'm Commander La Riviera, and then currently I am in Germany, in Kiel, as Italian Navy liaison officer in ThyssenKrupp shipyard within the submarine project U212. I hope next slides will come. Okay, some few words about my professional background. I'm a telecommunication engineering, and I was on board of Italian Navy submarine for around 8 years as a weapon officer. I have a master's degree of underwater electroacoustic on optics and quantum information, but I'm not a scientist, only a military engineer. Nevertheless, in this few slides, I will give you some peers about interesting topics which can be elaborated from companies to understand if this study could be in the future strategically important relating to the military world, and especially for the underwater domain. So let's start. In the last 10 years, nitrogen vacancy within the diamond has become extremely important for many applications in the field of quantum technology, especially in quantum sensing. The extreme sensitivity of this sensor and their stability allows them to be used in many areas. The magnetometers based on the diamond nitrogen vacancy technology have mainly 3 advantages compared to squids. First of all, they are very small because of the are not required cluttering cooling systems. They are height sensitive up to femtotesla. And the last but not least, we can obtain high spatial resolution up to nanometers in order to elaborate a real target image. So from a military point of view, we can think in the next future possible application of this magnetic sensor. First of all, in the field of anti-submarine warfare, unmanned vehicles could be integrated with adequately sensitive magnetic sensor that allow them to detect modern submarine. In this context, the sensor based on the diamond nitrogen's vacancy can be a key factor in the future operational scenario of the anti-submarine warfare fight. Then, in the field of mine countermeasure, we can load within the unmanned vehicle the latest generation magnetic sensor that could bring for sure advantages also in a mine countermeasure operation. In fact, the use of this magnetic sensor combined with a manned vehicle would significantly reduce the dangers to which military personnel are subjected during this type of operation. Moreover, within underwater surveillance, we can combine the use of acoustic and high performances magnetic sensor within underwater sensor array. The general performance of this sensor could increase, and the chance to discover and detect modern submarine will increase. So let's example is the use of high performance magnetic sensor within mines. This could be an enormous psychological factor on the opponent, avoiding any kind of intelligence action coming from the sea. Another particular field which could be in the next future very interesting for the military operation implication, such as, for example, governance and information security, is the underwater quantum communication. The technological development of quantum technologies for communication could allow to carry out a study of feasibility of photonic underwater transmission in seawater. For example, the use of blue, green, and green wavelength let a propagation distance between 50 to 200 meters in clear water. In this field, could be very interesting study the property of orbital angular momentum to increase the information amount transmitted due to the high dimensionality of this state that can be reached with this degree of freedom. This implies at the communication level a possible greater tolerance to noise and an increase in the security of the information protocol. So in the next future, could be analyzed and develop methods for the analysis and recognition of the received beam, verifying the transmitted and the received quantum correlation. This could be, for example, possible by using machine learning techniques useful, for example, to solve recognition problems, in particular noise environments, such as seawater. From an operational point of view, this short-range communication will appear covered in cipher and could be used within underwater network, where each node of the net, such as underwater vehicle or buoys or relay or submarine, should communicate without being discovered by the enemies. So thank you for your attention. This concludes my short presentation. I'm waiting now for any question, but if some question will born in the future, you can write me an email and I will try to answer you. Thank you very much.
Thank you very much, Simone. We are going to ask everything that is in our mind. Please feel free not to answer. I know there are questions that cannot or should not be answered, so please, in advance, I let you know that it's okay not to answer. Simone, the first question comes from the European Space Agency. Bruno Leoni, goedemiddag, good afternoon. What's on your mind? I think, Bruno, how you muted and we unmute.
Yeah.
I love your
Okay.
background.
Hi.
Yes.
Yeah, except I don't have thank you, Simone, for your excellent presentation. I wasn't aware that the Italian Navy was dealing with quantum sensing. I'm very happy that you are, and I was wondering whether you are already doing some practical measurements using diamond vacancies, and if so, who is your supplier?
First of all, I have never done any type of measurement with a quantum nitrogen vacancy magnetic sensor. It's only a study that I did during my master degree on optics and quantum information. So I'm very interested of this sensor, and I give some pills about this technological field that could be in the future very interesting for military application and operation.
I know of one supplier. If you're interested, I'm sure there are others, but the one supplier I know is Element 6, which is a subsidiary of the Bears, and they are dealing with diamonds for all sorts of applications, including high purity samples for NV applications. So Element 6 is, is if you want to start playing with some hardware, you can coordinate with them. I don't know if they're in the meeting, Jose, but they are definitely a good partner to have. Yeah,
they are in the meeting. They prefer to be anonymous, but now is when I tell them, okay, you want to join and come in. Now it's the time. But they're indeed in the meeting.
I'm doing some publicity for you guys.
But they decided to be anonymous. But thank you very much. Simone, one thing that for me is very interesting is when it comes to comparing the atom cooling solutions with other solutions. I know you have done feasibility studies. Is there any unmet need from the user side that you think can only be solved with either atom cooling or with either nitrogen, with either nitrogen vacancies in diamond, or are we thinking just more a blue sky research to see how far we can go?
Yes, this particularly of being very small and compared to other quantum sensor, for sure, it's a gain factor if we think in some operational scenario. Just I say before, for example, anti-submarine warfare. So using this sensor in other platform that are very small, for example, like a manned vehicle, could be so a good solution for this type of operation. And so we need a small sensor instead of big sensor.
The next question in the room comes all the way from Limoges in France. This company is making photonic crystal fiber glow photonics. Devang Naik, thank you very much for being with us today. Tell us, what's on your mind?
Hello, thank you, Simone, for your talk. And thank you, Jose, for organizing everything. If I could ask a question. So we develop, we have hollow core fibers, and we develop quantum sensors inside the hollow core fibers for magnetometry. One of the things we're really interested in is geolocation with magnetometry. And we're wondering if you're interested also in geolocation for submarine navigation.
Yes, for sure, it is also another field that where we are very interested in. If we think about platform which do not need of GPS signal to go where they are, and the submarine is one of the most significant example of that. So having sensor with an high accuracy and that will be so in meantime, so it will be with in a long time with high accuracy of the position, it would be very interesting. We know that there are a lot of study about inertial platform using atomic interference, and so we are now very interested also in this field.
Well, I guess the thing, so we're trying to go away from inertial sensing. So we can measure, for example, the minerals contents around you. And if you had an accurate map, geological map, then you could always compare, and you know you have precise geolocation. This is sort of the kind of things that we're interested in. And if anyone here is interested in this kind of technology, I would love to know more or talk more.
Photonics is very unique because you have your own towers to actually make the hollow core fiber. I went to visit them, spectacular drawing towers at Glow Photonics. Could you tell us a bit more on how this magnetometer works? So you have, yes.
Yeah, it's actually the oldest and most simple. We just use cold atoms, which we can now put inside these hollow core fibers. And well, we basically use one of our collaborators in Copenhagen, and we use sort of very special schemes of entanglement to be able to create non-destructive measurements. And this can allow us to easily get to femtotesla and levels. But the thing with us is our hollow core fibers are hundreds of microns in size. So we can fabricate really, really small quantum sensors with cavity enhanced, of course. So this is the thing that we would like to develop more, compact magnetometry.
One of the things that is very spectacular here is that the fibers of Glow Photonics have already been approved for space applications. So they are ultra sustainable for harsh environments, Simone. So this is a really interesting technology for the miniaturization of the quantum sensors. Just two more questions for you. The first one is coming from Quantum Nanoscience, QuTech in Delft. Toeno, what's on your mind?
Hi, thanks for the nice talk. I also had a question on these photonic fibers. If that's okay.
Of course.
So I wonder if you can, so they are hollow core, and now, you know, in a lot of experiments, you actually want to bring the light down to a nanoscale to couple to some nano device. Mm-hmm. And I wonder if you can actually pull these fibers using a fiber puller into a sharp tip and couple evanescently to some quantum device. I know this is done with normal fibers, but with photonic crystal fibers, I've never seen it.
Well, actually, one thing that we can do right now is you could take a normal fiber and we could mode match it to go directly into the hollow core fiber. So if you can, in principle, do this with a normal fiber into these things, then we could easily couple it to a normal fiber. But this is one of the things that we have this organization in France. Right now, it's just southwest of France, QuTech, that's also trying to develop this technology to couple the halocore fibers to nanofabrication to kind of make the bridge between the two. That's not something, so that's something in the next 2 years that we plan on developing. But for right now, we do have this other technology where we could easily seamlessly splice a normal fiber with the halocore and mode match the laser beam, the light between them. If that helps.
Okay, great. Thank you.
The next question comes from Bruno Leone from ISA. Bruno, what's on your mind?
Yes, I also wanted to ask a question to Glow Photonics. So we're still stuck with, for us, the comparison between NV centers and cold atoms for magnetometry. And so I wanted to know, how does your system compare in terms of performance between the two? Because we know that NV centers are smaller but less sensitive, and cold atoms are bigger but more sensitive. So where does your system fall in between the two? Or does it have the best of both worlds?
No, no one has the best of all the worlds, I guess. Well, okay, in general, cold atoms just have more atoms that you could kind of bring together, and they're easier to create squeezing and to create our very unique entangled state, which allows non-demolition measurements. But the main advantage is we have more of them. Now with us, as we try to bring a smaller, we have less atoms. So we in principle, we sacrifice a little bit. However, we encase all this inside of a cavity. So at the level we're at right now, we could take a 5 millimeter level size footprint and go down to 100 microns and still maintain the same signal to noise, which means we could arrive at sub-femtosecond magnetometry. However, if you're asking me if you go even lower, so 10 microns, that's a bit of an open question. Simply because our cavity trick that we use kind of limits at a certain point where the amount of light is really large and you have second order collisions. But at the level of hundreds of microns, it's the resolution, all the advantages that you have in a normal atomic vapor is still there.
Okay, so actually my question wasn't in the how small the cavity could be, but how small the actual device, the actual magnetometer device could be. And have you actually compared the performance of an NV center with your system? Or is it comparable at the moment, or have you not done this comparison? Because that would be a very interesting data for a choice, like for Simone, for example, if he wants to go for a small detector, he could go for this system. Also, depending on so size and price could be a big factor.
So we compared, for example, for 2 millimeter footprint atomic sensors, compared them to the NV centers, and this compares really well. We could get to sub-femtotesla.
Okay.
Now, we haven't compared the 100 micron yet. This is the big thing. However, one of the things, for example, we're interested in developing is for use with the quantum magnetic induction tomography to get brain imaging with good resolution. And one of the things that we noticed that even if your footprint is large, if you use a network and have this very particular networking, so say 200 sensors with a certain spacing and a certain, you could recover the spatial resolution that in principle you think you can't get because the footprint is large. So in this particular application,
I think a competitor is doing a system like this called Quanta in the UK. They're also using something like this.
They are. Yeah. Now they're operating a different frequency regime. So we want to operate in megahertz.
Okay. Let's discuss this offline. This is a global meeting. So we go from ISA in the Netherlands, in Europe. We go from that to Singapore to welcome to the meeting Leonid Krivitsky from A-Star in Singapore. It's great to have you here, Leonid. Please tell us what's on your mind.
Thanks. I have a question to Simone. I really appreciate your insights and user case. So my question is just like, if you mount a very sensitive system, a very sensitive sensor next to the submarine, I presume there is a lot of background noise from the motors, from the, all the devices that could actually create this very high background, right? So is that some of the problem that you might face there?
Yeah, for sure. But in the general concept, I believe that could be used. This sensor could be used also in an unmanned vehicle where we have not so magnetic materials such as submarine. Nevertheless, submarine now are not with a very heavy magnetic footprint. So, but it is a study. I think in the future we can manage both solutions.
Mm-hmm. Thank you very much.
For those of you who don't know, Leonid, this is one of the key people that we have in the quantum community. You know, PhD from Moscow, but he worked at Max Planck. I remember you also work in Denmark. I know you are doing quantum research now at A-Star in Singapore. Leonid, could you tell us a bit of what you are doing, and most important, could you tell us how the other companies could help you do it even better?
Yeah, so we work on two types of technologies. We work on integrated single photon detectors for visible light, where we use the silicon nitride waveguides fabricated at AMF, and we terminate them with silicon devices. So this is just an integrated platform for single photon sensitivity. And we're also looking at atomic vapor magnetometry for health applications and for geology. Right, and we try to, build some of the devices in-house to have a glass blowing facility and build that up.
This is one of the key areas on photonic integration for quantum sensors. So companies in the room like Q.ANT or QuiX, you have to get in touch with Leonid from A-Star. There is clear room for cooperation here. The time flies. The first 50 minutes of the meeting have gone by. I really want to start with one company in the quantum instrumentation and then one end user to get the meeting going. Because now we are going to go to the #1 R&D center in the Netherlands, perhaps in Europe, perhaps in the world. We go to the center, I call it QuTech. I know you renamed yourself, Simone. We go to Delft, so the Quantum Nanoscience Center, to meet Toeno van der Sar. Toeno van der Sar, who is one of the researchers that is working on quantum sensors. Toeno, thank you very much for being with us today. Tell us how the companies over here can help you do even better research that you are doing. The floor and the attention of everyone is Van Jou.
Thank you, Jose, for that nice introduction, and thanks everyone for joining this interesting meeting. So my name is Toeno van der Sar. I'm an assistant professor in the Department of Quantum Nanoscience at Delft University of Technology. And just to show a little bit of background, I did my PhD with Ronald Hansson at the TU Delft. Ronald Hansson is a professor that uses NV centers in Diamond to build a quantum internet. In my PhD, I worked on NV centers for building, say, mini quantum computers. I then did a postdoc with Amir Yacobi at Harvard, where we used NV centers to do quantum sensing, mainly focusing on material research. And since 2017, I'm in Delft, where my group uses NV centers to study spins and currents in materials at the nanoscale using NV centers in Diamond. So the idea of the experiments is like this. We have an NV center as a sensor, and we detect, we try to see where are the currents, the electric currents in materials, and where are the spins in a material by imaging their magnetic stray fields using the NV centers. So just to show you where we are located. So this is a picture of the campus with the physics building on the left. So this hosts both my department of quantum nanoscience. So we are a very explorative department, which is part of the Faculty of Applied Physics. We have several groups. We focus on quantum matter, quantum sensing, and quantum transduction. So if you are doing research on using a quantum sensor to study quantum materials like I am, this is really a great department to be. There's a lot of synergy with other groups. Now, in that same building, we host the Institute of QuTech, with whom we closely collaborate. So this is basically an overview now of the 3 Diamond groups in Delft. We have the group of Ronald Hansson, who works on developing a quantum internet, of Tim Taminiao, works on using NV centers as quantum registers. They are both part of the QuTech Institute. And then we have my lab that uses NV centers to do quantum sensing. So we really try to develop new ways of imaging spins and currents in materials at the moment. So these pictures were taken from say a popular science article that we wrote together and is published in Photonic this year. Now, diamond quantum microscopy in my lab focuses on two modalities. So we use on the one hand diamond scanning tips. These are like the tens of micron all diamond platforms with a small diamond nanopillar at the end. And then we can have NV centers just a few nanometers below the tip surface. And we can scan these NV centers over a material of interest, image the magnetic field with very high spatial resolution. So the nice thing about this technique, it gains high spatial resolution, like on the nanometer scale. But the challenge is that it is slow because you do a point-by-point measurement. So if you want to be faster, we do wide field imaging using a diamond by putting a diamond on a chip. So a very simple measurement geometry where we see here a 2x2 millimeter diamond that is full of NV centers, shallowly implanted below the diamond surface. So they act as our sensors, and we probe the magnetic fields generated by a chip. In this case, the chip is a magnetic film. It's called yttrium iron garnet. It's a super famous magnetic material which has very long wavelength, low damping for magnetic waves. So if you measure the magnetic field when you drive a microwave current, you can do that using the NV sensor, and you can see these waves. They're called spin waves propagating in the magnetic material. Now, these spin waves are at the center of the field of what is called magnonics. And the idea of that field is to use these waves to create logic, computational logic devices based on wave physics rather than on the diffusive motion of electrons. So we can image those waves. And the nice thing about magnetic imaging that is enabled by NV centers is that you can look through metals. For instance, you can look through the electrodes that you deposit on a chip. So here I show such an image. On the right, you see an optical microscope picture of an electrode on a magnetic film. And in the color, you see the magnetic fields generated by these waves that are excited using a current in this electrode. And you can just look straight through this 200 nanometer thick piece of gold, which optically is impossible, but with magnetic imaging, you can do it. And I think this is really one of the strengths of the magnetic imaging, is that you can look at buried materials on computer chips, for instance, or in more fundamentally in magnetic heterostructures. So I made one slide showing the opportunities and challenges that we face. So what can NV quantum sensing bring? Well, in addition to, I think, what was already discussed in this meeting, and the applications already discussed really focus on getting high sensitivity magnetic field measurements with relatively low spatial resolution, right? So you on the millimeter, on the micrometer, or the hundreds of micrometer scale. In our lab, we focus more on the nanoscale imaging of magnetic fields using NV centers. And that is an interesting application area, because you can look, for instance, at computer chips. Where does the current run through the wires? Where are the weak spots in the wires? They will show up in the magnetic field images of such currents. You can use the NV sensor sensitivity to microwaves to probe microwave frequencies, again at the nanoscale, or DC electric currents, or you can use it to probe the structure of magnetic materials. And I think also application-wise, this is an interesting direction, because you can see, for instance, magnetic domains on materials that are used for hard disk drives, to give an example. Now, to get a good diamond magnetometer, you need the following things. So you need a very good photon collection efficiency. Typically, we shine a green laser at these NV centers, and then we look at the far field luminescence. And the better you collect those photons, the higher your sensitivity is. So these kind of fiber-based magnetometers are very interesting, I think, because they allow you to potentially directly couple your luminescence into a detector. And that's why I was also interested in these hollow core fibers. But and also the APDs or the SSPDs sold by ID Quantique target this challenge here, and that's why I was interested in seeing if you can actually get higher count rates using some of these ID Quantique photon detectors than you can get with conventional APDs. Now you also need high quality diamond. This was already touched upon by Jose. Element 6 makes those, and that's really crucial because you want to start with a diamond with few impurities and then put a lot of NV centers in them, which are then high quality and give you a good sensitivity. Now, to use such scanning tips for magnetic imaging, what is also a challenge is to get the microwaves that you use to drive the NV centers to the tip. So an integrated delivery of microwaves into AFM probes is another outstanding challenge. And then there's a lot of work going on trying to bring this technique into the millikelvin regime, where a lot of interesting quantum effects happen. So the low temperature regime is the quantum realm, so to say, and the challenge with NV magnetometry is that the shallow NV centers that you like to use for sensing are not so stable at millikelvin. So there's a lot of research going on now trying to use different defects. But in addition to that, photon collection at low temperature is very challenging. So again, a fiber-based approach would be very useful. Now I'm working on this project where we try to bring quantum microscopy based on NV centers into or based on spins in diamond into this millikelvin regime. The idea is here to open up the possibility to see where the quantum currents run in quantum devices, such as superconducting qubits, for instance. And I do this in collaboration with these industrial partners. With that, I would like to thank you for your attention.
Thanks a lot, Toeno. Thanks a lot. That's very interesting, very amazing to listen about what you're doing there. I have a first question. Till I will let the audience decide when they want to speak, but I have a first question. You already said that you're using quantum sensing to improve quantum materials. So we're speaking about the self-improvement cycle there, no?
Your question is if we are speaking about?
You spoke about using quantum sensing, your quantum sensors, in order to improve quantum materials. Materials that you're already using to do the quantum sensors. So
that's right. So there are a lot of startup companies nowadays that develop materials that are based on quantum effects. And often those quantum effects lead to special properties at the nanoscale in these materials. Now, if you want to see what goes on at the nanoscale, you need a small sensor. And typically that sensor then acts as a quantum sensor because small things behave quantum mechanically. And that's why I think there's kind of a natural match between quantum materials and quantum sensors, just because you are interested in small scales.
Thank you. Thanks a lot. So another question?
So it's Nick Werstick here. I have a question on the wide field imaging, right? You sort of talked about imaging underneath the traces on a chip. Is there a specific use case you're kind of targeting there, like a problem that people are trying to solve? Like I've seen other groups look at NV as a way to fingerprint chips, right, for verification and things like that. Is that do you give a sort of an example of where you're?
That's a nice question. So in this. The field of spintronics tries to convert electrical signals, so electrical currents, into magnetic waves, and then and this is a growing field with devices that are really on the brink of becoming useful. So logical devices like transistors based on waves in magnets. And to excite those waves, people use electrodes. So if those electrodes have some detrimental effect on the waves, which they actually do, and that is the point of this of doing this work, it's nice to see that. And with NV sense, you can just look through the electrodes at the waves underneath and see that they are very strongly damped actually by the electrodes. So this was the new thing of this measurement. But I think more general, you can look at defects underneath electrodes on a chip. And that's also something that we did. You can review scatterers underneath electrodes, and which are difficult to see optically. It's a general principle of MRI, and that you can look into a body without being hampered by the opaque body itself. And this is also true for magnetic imaging of condensed matter systems.
Thanks a lot for your answer, Toeno. And we have another question from Yusef. Yusef, you have to unmute. Yeah.
Yes, hello. I have a question. Which of the current startups or enterprise that have some quantum computers use now this NV centers for quantum computing? Is it applicable now in the NISQ era, or it is still in research?
I would say the biggest application area of NV centers at the moment is not in quantum computing, but it's really in quantum sensing, right? So there are various reasons why you want to be able to sense magnetic fields. Some of them have already been mentioned, for instance, for positioning reasons or detecting mines in the sea. This you can do with a magnetic sensor, and NV centers are very good sensors. Also for material research, magnetic fields are contain valuable information. So material companies are interested in using microscopes like AFMs or SEMs to characterize the materials. And likewise, if you have a magnetic imaging microscope, you can learn valuable things about your materials. So I would say that is the main application area at the moment. Now, that said, there is also a lot of research activity on trying to develop NV centers into qubits. But I am not in that field, and I have to say I'm also not aware of companies actually trying to build commercially now a quantum computer based on NV centers. But
thank you very much.
I don't know.
Yusef is a person that is joining the meeting for the first time. So one of the big challenges in quantum is to keep the meeting on scope. It's talking about quantum sensors today, please. So I have a surprise for you, Toeno. You wanted to talk about microscopy, and we have from MPL, we have Melanie Hartman in the room. Melanie, good afternoon. I hope everything is okay. You are in the UK from MPL. We would like to know a bit about your interest from especially the microscopy area on quantum sensors. What brought you to this meeting? And we'll try to find some cooperation for you. Melanie.
Okay, great. Thank you, Jose, for the invitation. So I'm a product manager at MPL.
Can you speak closer to the microphone or louder? I think we have a problem with the sound.
Sorry.
Yes.
I always have a problem with Zoom.
It works great now. Tell us.
Okay, sorry about that. Yeah, so I'm a product manager. I work within the quantum technologies department. Also, sort of working in the quantum area is the time and frequency department. And one of the reasons I came along today, I was just interested in the sort of the ion trapping side of the presentations, because that's one of the projects that I'm working on at the moment with Alistair Sinclair, and we are part of one of the Industrial Strategy Challenge Fund projects. This is a big part of the National Quantum Programme here in the UK. So it's a large consortia of industry working to try and improve the supply chain asset around quantum computing in the United Kingdom. So we're part of that project. So I'm very much here.
My good friend Alistair Sinclair. Alistair, it's good to have you in the network. Melanie, could I ask you if there are some challenges when it comes to the fabrication, testing, space validation, space qualification, packaging, that perhaps other companies could help you, could add value to this strong consortium you already formed?
Yes, absolutely. Yeah, the packaging has been a real challenge. The making of the housing has been a real challenge. So we are definitely looking for other organisations that might be able to help us with that. And then, what was your other question to me? Can't remember.
No, that was good. The roof cooperation, and I also already know that the packaging and the space qualification. Do you have the idea is to bring this to TRL 5, which is a big challenge already to test it in real time, in real value conditions. What kind of application fields do you have in mind? And maybe some companies can help you for the validation of those application fields.
Yeah, we don't have in-house fabrication ourselves. We do have to work with other partners to be able to achieve that. One of the things that we are doing at the moment is something called measurement for quantum. Unfortunately, it's only available to UK companies, but if there's a UK company here who's having some measurement challenges sort of in the quantum area, and that could be absolutely anything, they can get access to 20 days of expertise and capability at MPL, and it's paid for by the British government. So it's a really, really good opportunity to access some capability that you might not actually have available, but we will. But if I just find the link for it, and then if anybody's interested and has a you can have a registered site in the UK. So you know, you might have your main corporation somewhere else, but if you've got a registered legal entity in the UK, you get access to it. I'll just find the link. And
the reason why I wanted to connect you with Toeno is because I was aware that there is no real manufacturing in the consortium, and Toeno is also representing the CAFLI Institute. Toeno, please correct me because sometimes I get lost with so many acronyms. Sorry about QuTech, Quantum Nanoscience, CAFLI, but in CAFLI is where you're doing the manufacturing of many quantum sensors. Could you tell us about the manufacturing capabilities of, in general, quantum nanoscience of CAFLI for ion trapping or quantum sensors? Because I think there could be some room for cooperation here, Toeno.
Yeah, at the moment, I don't believe we do any ion trapping in the CAFLI Institute. The quantum sensors that we do develop are based on spins in diamond and also on superconducting qubits and mechanical oscillators. So, for instance, the diamond structure that you saw, so the scanning diamond nanotip, we PhD students in my group make those in the clean room.
I want to make an introduction here because, Toeno, I want you to interact closer with the group of Alistair, with Melanie from MPL. They are doing a fantastic job on the metrology sector in the UK, leading the quantum tech. Thank you very much, Melanie, for being with us. I want to go now to one company that has made a big difference in EPIC entering the quantum business. We are talking about a Trumpf company. We are talking about a company that brought lithium niobate technology to answer quantum challenges. We are talking, of course, about Q.ANT. Michael Förtsch, CEO and founder of Q.ANT, is here with us. Michael, thank you very much for joining the meeting today. Tell us what you do. Most important, tell us how the other companies can help you doing it even greater. The floor and the attention of everyone, I love this company, goes to Q.ANT, goes to you, Michael.
Thank you very much. I hope it's not expected that I'm talking as fast as you are. It's very impressive how fast you transport information. See?
Oh, thank you. It's just coffee. Eh? No other secrets.
Coffee. So the typical question, I guess you see my screen, and in the meanwhile, in the full screen mode. Thanks for being here. Thanks for giving me the opportunity to speak. Yeah. So what we haven't made public so far, we have a vision. And the vision is we want to revolutionize the quality how machines analyze their environment, people notice information, and the way humans think. There is nothing about quantum, but these 4 bullet points perfectly summarize our activities, what we are doing. And on our day-to-day business, what do we need to do basically to achieve our vision? Well, we have to take care about photonics, and photonics dedicated for quantum technologies. So at our very heart, what we are experts in is the electron to photon conversion, meaning we have the skills in our team to convert photons, to generate photons, for example, frequency stabilized, super low noise because of our own electronic architecture, our own laser drivers, which we develop. This is the first sector of each of our developments. The second sector is the so-called quantum control sector. This is where the quantum states are generated, our superposition states, for example, for our particle sensor, or where we generate entangled states using what you already mentioned, where the entangled states are generated using lithium niobate on isolator technique, which we develop on our own as well. Now, and this is also the area where the light interacts mainly with the environment. So this, for example, in all our sensor applications is the part of our modules where, for example, they pick up the Earth magnetic field or the neuronal actions of a brain. And of course, photons are not as appreciated by customers as electrons or data is. We reconvert everything back into electrons with, again, a framework existing out of low noise transimpedance amplifiers, and in the meanwhile also FPGAs and a set of algorithms on industrial computers on an own developed board, which then reconverts the analog signals from photons back to electrons and then back to data. And in the end, this is what the customer appreciates. What have we done so far on the component side? Yeah, we developed our own laser modules, but honestly, we are not starting. So we are sourcing chip on submount, and then we package it internally in the Triumph Group. We do it partially on our own. We partially go hand in hand with other subsidiaries of the Triumph Group. And we so far developed three wavelengths on our own, 405, 520, and 795. In the quantum control sector, we are cooperating mainly with other companies. For example, we are allowed to talk that we are cooperating with Bosch here on a particular type of gyroscopes. But we are also undertaking our own developments, mainly in the sector of nonlinear waveguides. What you can see here is the result of 3 years of development. This is lithium niobate on isolator, on silicon mainly. We basically buy the wafers externally, and from then we own the whole process chain in order to generate those waveguides, including periodically polling structures. And in the last sector, you see parts of our electronic boards and also the receiver optics, which we develop, for example, for parts of our particle sensor area. Now, already addressed, we want to go to markets. This means we need to solve problems at the customer. So far, we only solved components issues. What we are currently pursuing, we are pursuing 3 routes internally. The first one is the particle sensing area, where our sensor uses superposition states of light in order to analyze liquids or gases. It's either way, the system can analyze both, which is quite unique. In addition, it can measure with a single measurement the speed, the size, the direction, and also it can, in the meanwhile, identify the shape of the particles. Because we are generating, I don't know how many times more data than a typical light-based particle sensor is doing. And by this, we are training our own neural networks, for example, to perform shape recognition. Everything is done in real time. So we have a refreshment rate in the megahertz rate. And everything, one has to mention, is operatable at room temperature. And for our customers, it's highly appreciated that they can either work on our software API, or as well, we have a hardware API to let our customers integrate into our system. The second path which we are pursuing is the magnetic sensing. This is in strong cooperation with Bosch, for example, where we use diamond-based NV center magnetometers. And I've also indicated the TRL level. So while with the particle sensor, we're close to a serial product. So the serial product launch will be next year in the first quarter. We are in the particle sector already with customers by renting prototypes to customers to get experience with the systems in the field. The magnetic field sensors take some time because we need to do much more fundamental work here. This is also a field where we are actively searching for cooperation. because what we want to realize here is this is something which we already are funded from the government, is, for example, using magnetic field sensors to control exoskeletons of disabled persons. So there has been a use case which was qualified, and we've been granted a project here in the context of the Zukunftscluster, the future cluster here in Stuttgart area. It's called QSense. And our part is together with companies and a clinic to develop such a sensor and demonstrate the first motion of an exoskeleton. And the last part, I think it was in the press, it's not about quantum sensing, it's about quantum computing. But yes, what you can see here, Tobias, one of our engineers, is holding a 3-inch wafer, which contains, I think, 40 chips, all lithium niobate, which then shall in the future be used to become parts and components of quantum computers. The big asset, of course, of photonics computing in general is that the chip itself can be operated at room temperature in contrast to other platforms. Of course, the detectors are not, they have to be cryogenic. But what are partially our features is that we have super small losses per centimeters on these devices. And we already started to integrate modulators into the waveguides. And by that, plus the periodically polling, we can offer from the pair photon source until the end of the network, until close to the detector, a monolithic design. Yeah. The question was, what do we offer? Well, of course, we offer partially already some products. We offer market-oriented quantum technology. We offer particle sensors in the meanwhile. We also offer nonlinear waveguides based on lithium niobate and isolator. And in general, as a development partner, we offer high expertise in the field of photonics, quantum technology, electronics, and software development. And what we are always looking for is strong partners in the context cooperating. Let's drive quantum technology to markets. We are searching actively for partners along our value chain. We are not intending to do everything on our own. Actually, it's the other way around. We have distinct expertises, but we are more than happy to partner, and as well along the value chain, but as well on the side of the end customers. And since we are quant, we are calling ourselves the quanties. We are continuously searching for new quanties. I hope it's okay to have this large site. We have a campaign running on the social media. If you're brilliant, start at Quant. We'll hire you for sure. Thank you very much for your attention.
I don't know if I'm brilliant, but maybe I'll send you my CV. I really love this company. You guys are really, truly fantastic. For those of you who know me a little bit, they know how much I'm excited about lithium niobate on insulator being manufactured in Europe. I am really excited about this. I want to make a round right now about how we can use photonic integrated circuits for quantum sensing. But before that, I would like to give the floor back to Amir from CSEM, because I would like for everybody to know about his plans for having lithium niobate and insulator manufacturing in Europe, which are not plans anymore. It's a reality. Amir, tell us a bit.
Yeah, let me share my screen real quick. It's actually, I have only 2 slides here. Can you see?
Crystal clear.
Wonderful. Yeah, thank you so much.
Go to a slideshow mode so we can see it bigger even.
It is loading. I don't know. Can you see it?
We can see it well enough. Yes. Now you are showing the wrong screen. So display settings and then mirror it.
So let me. Okay, just give me 1 second. Okay.
Go to the.
Oh, sorry. You're still not seeing, huh?
And we are okay time-wise, so don't worry, you can do it. And afterwards, we will address the questions that we have from Globe Photonics, from Air Force Research Laboratory in the US. By the way, the Air Force is joining today as well. But first, let's talk about lithium niobate and insulator. Amir?
Yeah, I'm struggling here. One more second.
Oh, relax. You managed to do MPW lithium niobate. You can share your screen.
Okay.
We can see it clearly. Just go ahead. It's fine. We can see it.
Is it good now?
Yes.
Or is it wrong page?
It's fantastic now. Don't touch anything.
Wonderful. Okay, thank you. So thank you, Jose. Yes, I want to also briefly introduce our activities on actually lithium niobate and insulator. Indeed, at CSEM, we are quite interested and active in this field. And just for those of you who don't know CSCM is a research and technology organization based in Switzerland. Our headquarters is in Neuchâtel. And what we got actually interested in lithium niobate and insulator platform, around 2 years ago, and we have a sort of a long history in photonic integrated circuit at CSCM. But particularly, we got interested in lithium niobate for a variety of actually reasons. Initially, because of nonlinear applications, but later on more and more for electro-optic properties of lithium niobate. And mention very quickly our vision in long term is actually to develop the first foundry. Lithium niobate, I think our colleagues actually already sort of advertise why it's so interesting. It's a very interesting material, but the downside is like right now there's no foundry anywhere in the world, especially not in Europe, that actually offers this as a technology in MPW with a process like a PDK. And this is what we are trying to change at CSCM. So right now we already have a platform and we're already offering this shipping actually cheap across Europe. But lithium niobate for those maybe just a one slide sort of reminder of the properties of lithium niobate. Lithium niobate comes with this intrinsic electro-optic coefficient, which means that actually we can modulate very efficiently and very fast. By fast, I mean with frequencies well above 100 gigahertz, and actually people also us demonstrated modulators with VPi below 1 volt. It also comes with a very strong Chi2 and Chi2 nonlinearity, so we can actually do a lot of nonlinear functionality such as the second harmonic generation, wavelength conversion, and also in Chi3 you can do super continuum generations or even Kerr comms. At the same time, actually, it has a very wide transparency window, so we can actually cover the entire wavelength range from 350 nanometer to 5.5. This large band gap also allows us to operate at a relatively high power. We can handle high power without the issue of two-photon absorption. And at CSCM, we already developed this technology. We can actually achieve optical losses quite decent. We can almost guarantee better than 0.2 dB per centimeter. And another aspect about lithium niobate, it also has a very strong sort of AOM, let's say a piezo coefficient, so you can actually envision components such as acoustoptic modulators. So right now CSM has already sort of have this platform. This is a work in progress. What we are working these days, obviously, in addition to improving our process flow, is on a PDK library, so a process design kits of several building blocks, active building blocks such as MZIs, tunable resonators, phase shifters, but also PPLNs, as well as several passive for interconnecting. So actually designers in industry can actually take these building blocks and then build more complex. On the top right, you can actually see the cross section of our sort of current offering right now. We have two levels of actually sort of waveguides, one optimized for 1550. One optimized for the second harmonic at 780 that's monolithically integrated on the same platform. Actually, right now it's not shown here, but this is we have two levels of metallizations for interconnecting and few of the SCMs. So we already have this. It's sort of we are offering this as a pre-commercial service already. We are very interested in the field of quantum, and we have a lot of projects with some of the company or set of partners.
Entire PDK with the standardized building blocks, active and passive, that operates at 1550 and 780 nanometers. So this is something that is big. So I would like to first of all go back to Q.ANT. Michael Förtsch, there is I think it's good news that we're going to have a foundry of lithium niobate on insulator in Europe. What would you ask that foundry? Because of course you would like to have manufacturing in Europe for your technology. What would you ask them? What would be the first thing that you say? I'm concerned, I need you to provide this.
Well, the first question is, Amir, where have you been 2 years ago?
Developing in the lab.
No, honestly, I'm more than happy that we meet here at EPIC. Now, Jose, you must be very proud that I said this sentence, but it's true. We should talk. This sounds really great what you have. The values, I mean, for us, mainly the damping values are what we've been fighting for 2 years now, and what you have and what we have seems to be comparable. And it's absolutely great that you offer a foundry service. let's directly start talking how we can work.
Absolutely, we can start right after this. Maybe just add one thing that actually maybe one difference is that we are doing it at 6-inch. So, and we can actually already handle the smaller scale productions to around like 200 wafers a year in-house in our clean room. But we are really looking for other actually sort of bigger foundries for larger scale, which comes after, next step after the MPW.
Amir, Michael, and also from Quicks using silicon nitride, we also had John Epping. There's a person I want you to meet. Coming from the other side of the Atlantic, the Air Force Research Laboratory today is represented by Brian Cash. Brian, good afternoon here. Good morning to you. Brian? Let me see, we can hear Brian. This is the thing of making the show live and connecting with the Air Force Research Labs. Brian Cash, good morning.
Can you hear me now?
Loud and clear. Yes, we could hear you and then you muted again. So let's see if you can unmute again. Yes, we can hear you now, Brian.
Okay.
Yes.
All right, sorry about that. Yeah, I was just asking if I heard correctly that that you were making optical isolators with lithium niobate on silicon.
No, this was, no, we are not making optical isolators. We have lithium niobate on isolator, meaning that we have a photonics material, lithium niobate, directly bonded onto the workhorse of electronics, which is silicon. We can, by the way, we can bond it on any material you wish, because this is a laser-based bonding process. But out of convenience reasons, we did it on silicon wafers.
We all.
Okay, my apologies, bad audio on my end.
Brian, we all, everyone in photonic integrated circuits, including Martin Schell from Fraunhofer HHI, we all are dreaming about an isolator on chip for photonic integrated circuits in all the platforms, in silicon photonics, in indium phosphide, in silicon nitride, in polymer, you name it. We are dreaming, but I know that there is some work in Berlin at Fraunhofer HHI for isolator on chip. I have Martin Schell, the director of the institute, on the line. Martin, could you give us a bit of an update? Is there some work on that respect, isolator on chip?
No, sorry, this is not isolator on a chip. This is isolator integrated into a single mode waveguide platform, our polymer platform, but it's not integrated, monolithically integrated. So what we do is have two single mode waveguides. We make with grin lenses a small free space region inside a single mode waveguide PICs. And in this 1 to 10 millimeter free space section, we can put various things like isolators or nonlinear materials and so on. So that's the isolator went down to 1 dB excess loss, which is quite a good value, but it's not a monolithic integration like I think the question from the Air Force person was targeting at. But it works.
What I can tell you is that I think the demonstrator, it works and is really small enough on the form factor that that is interesting for the industry. Brian, we have a lot of developments on hybrid photonic integrated circuits integration, polymer with silicon, silicon nitride with indium phosphide. It's quite a strong, this community in EPIC, and I know you have some challenges on that. We will address this on the next meeting. Brian, thank you very much for joining. And it is 4:30. And we saved the best for the last. We had a lot of problems today. I had to admit this. We had a lot of problems today with the IT, but we managed to have our keynote speaker on the line, Janine from Bosch, who is the person in the lead for the quantum sensors. Janine, good afternoon.
Good afternoon. I hope you can hear me well.
You know, your voice is making me goosebumps. Our team has suffered so much to make sure that you are here, and you are here. I know we had a lot of problems with Zoom, but we managed to solve. Yeah. Everybody can see your slides. Everybody can hear your voice, the floor, and the attention of everyone goes to our keynote speaker today, Janine Riedrich-Möller. The floor is yours. Just say next slide when you want me to go to the next slide.
Thank you very much for the invitation. I'm really happy for having me here, and I'm really happy to present you our activities on quantum sensors at Bosch Research. Next slide, please. So let me first briefly introduce the Bosch Group. You probably know us. So we are active in 4 business sectors. The largest one is mobility solutions, and then we have industry technology, energy and building technology, and consumer goods. And Bosch has a sales revenue of about 70 billion euro and has approximately 400,000 associates worldwide. And Bosch is very active in research and development. So we have about 73,000 associates working in research development, including 34,000 software developers. And we are investing 5.9 billion euro in research and development. Next slide, please. And one activity I'm working on is quantum technologies at Bosch. So we have one research activity in quantum cryptography, one in quantum computing, mainly on material simulations. And me and my colleagues, we are working in quantum sensing to sustain the leading position of Bosch in the sensor business. And we are mainly focusing on 2 products, so on magnetometers and on gyroscopes. Next slide, please. Let me briefly go more into detail. So for these magnetometers, we're using defect centers in diamond. They have already been introduced. They are sensitive to a magnetic field, and in scientific applications, sensitivities down to the picotesla per square root hertz has already been demonstrated. The second application we are looking into is an atomic gyroscope. So here we're using the spins in an atomic gas to sense the rotation rate of objects with really high precision. And the applications range from various fields, from automotive applications to avionics, or even to space applications. And there has been scientific applications in all these fields, but there are industry challenges, of course, remaining, downsizing the system to a small package, scaling to high volume production at a competitive cost structures. And we are expecting quantum technologies to really push the limits in sensing by reaching unprecedented sensitivity and accuracy, and with that to leverage the application to the next level. Next slide, please. Now I would like to go more into detail. So the NB center has already been mentioned, with these discrete energy levels that can be optically excited and read out, and that are sensitive to a magnetic field. And so we are using optically detected magnetic resonance to sense the magnetic field. And the advantages are it works at room temperature, it has a large dynamic range, and you can sense the magnetic field in all 3 directions. Next slide, please. So here you see our developments over the last years in improving the sensors and our prototypes in terms of sensitivity and functionalities. So in 2019, we had a sugar cube size sensor with a sensitivity of 3 nanotesla per square root hertz, which used an LED as a light source. And this year we published this demonstrator that uses a laser coupled with a fiber to the sensor head with a sensitivity of 300 picotesla per square root hertz. And when you look in the detail how the sensor is set up, then you see at the center a diamond with the optical fiber on top. Beneath the diamond, this is this very small rectangle. You have the photo detector mounted on a readout circuit for signal processing, and to the left you have the connector for the microwave field. So these are our activities on the diamond magnetometers. And let me briefly also introduce the atomic gyroscope. Next slide, please. So this is the other application we are looking into it. So here we're using the spins in an atomic gas for rotation rate sensing. The spins is associated with a magnetic moment, mu, and when you place this in a static magnetic field, it starts to precess with a frequency referred as Lama frequency. And this Lama frequency, omega L, it's basically proportional to the magnetic field, with gamma a gyromagnetic ratio as a proportionality factor. And when you apply now a rotation rate, this adds to the intrinsic intrinsic Larmor frequency. So by measuring omega L and controlling very well the static magnetic field, you can reduce the rotation rate. And in reality, we do not only use one gas, but a gas mixture of rubidium and of xenon. We pump it with a circular polarized light and initialize the system in a static magnetic field, and then we read out the system by a faint probe laser, and we drive the system by AC magnetic fields. And next slide, please. So here we are in a research stage still. So this is the demonstrator we're currently building up on a breadboard. The key element is the vapor cell shown at left, which we fabricate in-house using MEMS technologies, and these are filled now with rubidium and with xenon, our gases. And this vapor cell is mounted at the center of a miniaturized magnetic shielding that you see left bottom with a triaxial coil system inside. And of course, you need lasers for excitation and for readout. Here we are collaborating with Q.ANT in a public funded project, and you need, of course, detectors and optical components and electronics for signal processing and readout. And with this, I'm already at the end of my short introduction on quantum sensors activities at Bosch, and I'm really thankful for having me here and presenting our update.
After such an amazing presentation, and you say thank you. And I don't know how to thank you because I have to reveal it has been, she is connected by the phone of Antonio Raspa, who is holding it next to the microphone of his computer. And we tried every other solution to connect Bosch to Zoom today. Was very difficult. We have a lot of questions for you. I also would like to ask about the cooperation with Q.ANT, but I want to be fair. The first question has to come from one of my idols, Martin Schell from Hofer HHI. What's on your mind? You're muted. I have a mug to celebrate such accomplishment.
Thank you very much for the excellent presentation, really impressive. I have a detailed question. These vapor cells with this 1 millimeter by 10 millimeters, do you manufacture them in-house at Bosch or do you buy them? And if you buy them?
We fabricate them in-house in our clean room.
So you manufacture them yourself, yeah?
Yeah, exactly, yeah. Mm-hmm.
Thank you.
The first thing that I would like to ask, we had a meeting in Barcelona 2 years ago, the last time we met. Then the whole world fell apart, and now apparently it's coming back in pieces again. So Janine, we talked a little bit about a roadmap for the miniaturization of the sensor to be used in other application fields. Could you give us an update on the state of the art? And most important, could you give us ideas on how to have a miniaturization of the gravitometer based on diamond that you were working on?
On the diamond we are working on the miniaturization. So currently these are built up on discrete components like the diamond and the photodetectors and the microwave resonator. Of course, you can think of to miniaturize that even further, or in a last vision to use CMOS integration technology to shrink down the sensor head to very small volume and integrate this via CMOS technology. Yeah, this is really a long-term goal, so to say.
I was very excited to see that you are cooperating with Q.ANT, which I already revealed how much I love the company and I love the technology. Could you tell us a bit about how you are using the lithium niobate insulator? And then I would like Michael to comment on it. But first, could you give us a bit more details on the pump and probe lasers that you are using in cooperation with Q.ANT?
Yeah, we are cooperating in the project Milliquant, which is a public funded project funded by the BMBF and the national funding. And we are working at a wavelength of 795 nanometers and with a narrow line width, like I think 5 megahertz line width. And we have a pump and a probe laser integrated in one module.
Michael, I am very, very happy to see this cooperation. Could you give us some details how you are using your platform for these pump and probe measurements on this project?
Sure. First of all, it's you can really think about that in these projects we are acting as one company, and while Bosch has a lot of expertise in the MEMS business and the rubidium, We discuss what shall be the laser parameters, and not in the gyro project, Janine, but I think for in the other project with a diamond, we developed I think 3 or 4 iterations of green lasers, each of them improving on, for example, the noise stability, which meant to us we as well modified the laser chip continuously over 4 iterations and adopted the electronics to meet the requirements of Bosch in terms of noise stability of the green laser. And the same thing is what we are currently doing in this pump probe experiment here. So we discussed the specifications that shall be optimal for such a device. We built the first functional model, how we call it, tested in a joint laboratory, mainly in Renningen, close by. This is when I said I can jump over to Janine, which is 10 minutes away. And then we discuss the results and define next steps in the next iteration for the electronics and the laser.
I really can't thank you enough for what you are doing here, Michael, for the lithium niobate insulator. But I want to go, Janine, I'm going to go from Stuttgart to Limoges in France, because the next question comes from the hollow core fiber manufacturer, Glow Photonics. Please tell us, Devan, what's on your mind?
Well, thank you, Janine, and also Michael, for your presentations. And your vapor cell is really interesting to me. And my question is, would increasing the optical path length in your vapor cell technology help for your sensors? Because we have a technology with our hollow core fibers where we can increase the optical path length without using a cavity.
Okay, so you fill the hollow core fibers with gases. Is this the idea, or?
It's the idea, and it works really well with noble gases because the noble gases are more immune to wall collisions.
Okay, I've never actually thought about this option. Yeah, it's really an interesting point. Yeah. Okay. Yeah. So you can directly guide the light through your hollow core fiber and excite the atoms and read it out. Yeah.
And also we maintain strong coupling throughout the entire length. So for example, for a small length, we could maintain the same level of interactions like a cavity QED with the finesse of 100 to 1,000. Now,
okay, great. Yeah. Thank you very much for your input. Yeah, that's really an interesting point. Yeah.
Janine, you're working at 795 nanometers, correct?
Yeah.
95.
So 795. The losses at 795 are really low on hollow core fibers, correct?
Very, very low. Well, in principle, we can make whatever losses we want. However, it's not that broad. So if you make it for 795, it's difficult to put 900 nanometers in there. But for whatever wavelength, it's very small.
Might I directly ask a question?
Please go ahead, please.
Yeah, it's great because I saw your post in the chat because you said, would the optical path lengths help us? Yes, it would in terms for us, because then we could probably reduce the optical power for the pump laser. This would be, of course, favorable. However, what is the coupling efficiency you typically achieve? Do you have any rationales at hand for 795? Because at least I had back in my time experience in the mid 10th to work with hollow core fibers, and the coupling efficient or coupling light into the fibers was not the efficient process on earth.
Well, actually, what we do now is we couple into a normal fiber, and then we mode match that fiber into a hollow core fiber.
Okay.
And in this case, we could get really large. We get 80 or above coupling efficiency for 780.
How would this work if we would deliver you a pigtailed laser on a board, let's say a butterfly package pigtailed, including fiber? You could splice it onto your.
We can. So we actually have a product. We call it the microcell, which is a hollow core fiber filled with rubidium. We can fill with other gases and also with inputs for optics also. So, for example, for your probe laser beam itself. So one option is we could also just deliver this to you, or the other option is what you mentioned.
Okay, I see. Sounds great.
Janine, I would like to ask you back on the diamond. We had in Barcelona quite a strong debate about the difficulties in the supply chain for a diamond. Element 6 is in the room, in the private part of the room, but it's in the room. How does it look like now, the supply chain for diamond? Is it easy or difficult for you to obtain the material?
Yeah, there are a few suppliers for the diamond with the NV center of high quality. That's right. Yeah. So yeah, when we're looking into collaboration, then the diamond with NV centers is one part that we are looking into it. Yeah.
When we excite the diamond with the microwaves, later on you used some certain photodetectors to combine to get the different changes in gravity. Could you tell us a bit about these detectors, and maybe there is some room for cooperation here with the room?
Yeah, so they should be low noise detectors, and yeah, ideally it's a balanced detector. Yeah, for both application we use a balanced detector. Here for the NV center we use one arm that is detecting the laser light source, and one arm that is detecting actually the fluorescence of the diamond. And for the other application we also have a balanced detector where we use the probe laser beam, and that is detected via a Faraday rotation. So we use a balance detector, and the beam is split and sent to a balance detector. Yeah.
Is there the sensitivity or the noise floor of the detectors a challenge? Are you looking perhaps of some collaboration on that respect?
Yeah, exactly. Yeah, that would be great. Yeah, to have detectors with a very low noise floor, that would be optimal. Yeah, to reach these sensitivities that we are looking into it for the sensor in general.
And the final question, because I have in the room companies who have platforms based on silicon nitride that can provide ultra low losses, like really low losses. I'm talking about 0.1 dBs per kilometer on a chip. And we talk a lot about the integration plans for the sensors that Bosch is developing. Are you considering photonic integrated circuits as a platform for reducing the size, or is that something too far-fetched at this moment?
It's in the future, but nevertheless, we should, it's an interesting point to talk to partners and to look for further photonic integration of these sensors. Definitely, yeah, that's an interesting point.
Anton Stroganov is here all the way from Switzerland, Lausanne, beautiful city next to the lake. Anton, tell us about LigentTech silicon nitride platform. We talk about miniaturization, reduction, but here in the quantum sensors, we are thinking about low losses because we need to integrate optical path length difference. How could you help?
Yeah, indeed. Thanks for giving me a word, because I believe it was a lot of words today about lithium niobate, and I believe it's great to see how it's raising. But also we should remember that there are many different platforms, and each of them, they have their own benefits and their drawbacks, let's say. And just to remind everybody about LigentTech, just a couple of words. So we are a chip manufacturing provider, and we aim to be your innovative partner in the domain of integrated photonics, silicon nitride-based integrated photonics. And we have rather unique expertise with different thicknesses. We can go even thick in silicon nitride, which means that you can achieve really ultra low loss in different domains, including telecom. And also you have easy access to dispersion engineering, nonlinear applications, and so on, which can be especially interesting within the scope of today's discussion. And of course, we can discuss with any partner who may be interested with that. But just to address several other things, many times today I heard that it's really challenging sometimes for integrated platforms to have a good coupling efficiency. And here I need to say that we especially put a lot of effort into allowing good couplers and spot size converters. So at telecom wavelength range, we already achieved it, and we provide a special module for packaging, for efficient packaging, which is alignment tolerant, highly reproducible, and low loss with standard fibers. So in this sense, we're progressing a lot. And otherwise, just being compared with lithium niobate, I need to say that, as you may know, silicon nitride is much more mature in the sense that it's CMOS material, and it's scalable, it's stable, and it's easily accessible. And probably you already have seen, it was publicly announced recently that we now collaborating with X-FAB, creating the largest capacity silicon nitride photonics foundry in Europe.
Congratulations, Anton. 200 millimeter wafer manufacturing at X-Fab on silicon nitride starting January already, like in 2 months. This is fantastic, Anton. You know, Janine, actually, the silicon nitride platform has already proved reliable for quantum applications. And I have here John Empin from Quicks. John, could you tell us a bit what you do? I know, I try to avoid quantum computing and talk about quantum in general, and see how maybe you could help the further plans for reduction of the quantum sensors of Bosch and the other speakers.
Yeah, so what we are doing, we make the largest silicon nitride integrated photonic processor for quantum optics. So we're talking about really complex systems. Currently, we have something like 150 tuning elements on a chip to achieve with that really high fidelities. So what we're really looking at is our complex photonic structures, and to tame them. That's our core expertise, and that was also why I was interested here to see what possibilities there are for coupling silicon nitride, because also it's compatible to the wavelengths we've seen there.
Thank you very much. And by the way, John, congratulations on what you're achieving with Quicks. Janine, before I let you go, I'm a huge fan of the NMR work that you are doing. I would like to ask a bit if it's possible to tell us a bit about the laser module. You're always talking for narrow line width, tunable laser. What would be the Santa Claus Christmas list laser that you would like to ask next 24th of December?
Yeah, so for these atomic gyroscope, we need a laser that is resonant with the rubidium length, so either at 785 or 95 or 780 nanometers. A narrow line width means a few megahertz, and tunable, that would be optimal. And yeah, it should be compact because the smaller the laser module, the smaller the sensor can also be.
When you talk about tunable, you talk about constantly tunable, like a swept, or is it okay to have a discrete tunability?
Yeah, so the pump and the probe, they are slightly detuned by a few gigahertz, and so this is this I mean with tunable to set the pump and the probe to a line that they are detuned with respect to each other.
If anybody can help with that, I know it is a challenge to provide that laser, so anybody can help, which I know they can, and I will want to introduce them to you by email. Janine, you made a great effort to join today. I really appreciate.
Awesome.
Apologize for the IT challenges. We have a question in the room coming from Amir. Amir, tell us.
About this tunable lasers at 780 nanometer. I mean, Janine, thank you so much, because this is again an area of quite an interest for us, and we're working toward that. If you can specify the tuning range and the line width, more quantitatively, like and the power also, like the output power.
Well, the power, it's like 10 milliwatts or 20 milliwatts, something like this, and not very powerful. And then the line width is in a few megahertz. That would be great.
Okay. Yeah, I'd love to connect you, because I think this is quite close to some of the specs we're shooting at.
The next question in the room comes from Lars from NanoPlus in Würzburg. Lars Hildebrand, what's on your mind?
Yeah, I think it's not a question, it's an answer to your question, who can provide these lasers. So these lasers, they can come from NanoPlus, same as from Heinrich Hertz Institute, from Martin Schell. So so they are available on the market already, exactly for this application. Just give us a call.
No, you're already talking. But okay, Lars, thank you very much for that. Martin also has a comment or question. Martin from Hofrecht. I know he said that he's already answered by the comment of NanoPlus. Finally, all the way from Copenhagen, NKT Photonics. I love this company. Förtsch, what's on your mind for Janine?
I just wanted to comment as well that lasers at 780.24 nanometers are already available. We can offer up to 7 watts with killer or sub-kilohertz line width. I'm not sure if that's kind of overkill, and I would be curious to know what small needs or what small's footprint is required in your perspective.
I would like to say that at this moment, Janine has shared enough, and the next stage is to share privately, one-on-one. I know what she wants is not what you have in mind. There is an iteration on the, I shouldn't comment, but this is something that the two of you have to discuss privately. But I think there is huge room for cooperation. Janine and all the other speakers, first of all, congratulations. And second, thank you for bringing EPIC closer to quantum. Both Panagiotis and me are quantum fans. Being in these industries together has made a big difference. It is 5 o'clock. We start and we finish always on time. Thank you for another fantastic afternoon. And that concludes the public part of today's meeting. If you are in our Zoom room, our informal private discussion is about to start. I call it virtual drinks with friends. And we all know follow-up is important. But for now, if you are watching on YouTube, that's where we leave you for today. Thanks to the EPIC production crew and our sponsors for making today's event possible. More details about upcoming meetings are on our website. And if you want to get in touch with any of the participants, all you have to do is contact me directly and I will make sure you get introduced. It is all about connections. Thanks for being EPIC.